So I want to compare and contrast SN1 to SN2. So hopefully this fits well. I'm going to make a column here. And then in the space to the right of that first line, I want to divide it somewhat equally. And we'll do SN1 on one side, SN2 on the other. I like SN2 first for some reason. So SN2 and then SN1. So first part is just our rate law. So we'll write that over here. So remember SN2, my rate law, the rate equal rate constant, concentration of my alkyl halide multiplied by the concentration of my nucleophile. We can add reaction order at the same time. So reaction order, this is a second order reaction, right? That's what the 2 in SN2 stands for, it is second order. My SN1, my rate law only includes my alkyl halide. So my nucleophile is not part of that. It is first order, right? It is unimolecular. That is what the 1 in SN1 stands for. So second order versus first order. Let's look at our energy diagram. Try to fit this in here kind of small. So SN2 is concerted, right? There's only one step in that energy diagram. Energy increasing, reaction. So reactants, my transition state, and my products. You can add activation energy and your overall energy change if you want. My reaction, again, my energy. Because this one takes place in 2 steps, right? It involves a carbocation intermediate. So we're going to go up, we're going to come down a little bit, and then we're going to go back up before finally getting our products. So my reactants, my intermediate, and my products. Let's look at the mechanism. We are going to fit this in here. So I'm just going to use a secondary alkyl halide with both of these. But remember with my second order reaction, right, both of these are involved. So it's taking place in one step, right? It's concerted. So that nucleophile is adding at the same time that my leaving group is leaving. Because of that, it has to happen via backside attack. So my nucleophile needs to be opposite to that leaving group. And then that would get me my substituted product. With my SN1, my leaving group is going to leave first. I'm going to then go through a carbocation intermediate, and then my nucleophile can attack that carbon, getting to my product. So this one, backside attack, we need to add that note to it. We could add a stereochemistry column or row, stereochem, right? We're going to have inversion of configuration, right? If I started out with R, we end up with S. We start out with S, we end up with R because of that backside attack. This one, kind of our special note, is we have a planar intermediate. So from a stereochemistry standpoint, if it's chiral, we get a mixture of stereoisomers. If it only has one chiral center, it's generally going to be a pair of enantiomers. carbocation rearrangement. No. Possible. Right? No for SN2 because it doesn't go through a carbocation intermediate. You're only going to have rearrangements possible when you actually have a carbocation intermediate. So not possible for this one. I did leave the products off on the mechanism up above just because I ran out of room. When drawing a mechanism though, please make sure that you include the products. The identity of our alkyl halide. So for SN1 or SN2, sorry, we're doing SN2 first. My methyl group is better than primary, which is better than secondary, which is better than tertiary. And again, we're not even going to include tertiary. It's always nice when I give you a set of reactants if it's a primary or a tertiary alcohol, because you can just rule out one type right from the beginning. And then for these guys, we're going to have tertiary being better than secondary, which is better than primary, and methyl. And primary methyl, we're just gonna cross right out, right? It's way, way better than those. It's also good with allylic and benzylic. You could actually put those with, if you were to rank them, right with the tertiary. Maybe even better. And you can have, because they're not sterically hindered. Ooh, it just won't fit if I write can have, so you do also allylic and benzylic. Leaving group, faster with better leaving group, faster with better leaving group. Right, since the leaving group, right, the halogen attached to my partial positive carbon on my alkyl halide, that leaving group is involved in the rate determining step of both of those. Faster reaction for both if the leaving group is better. Our nucleophile, we want a good nucleophile, right, charged with an SN2 reaction. My nucleophile is part of my rate determining step. A neutral nucleophile or a good nucleophile, either way, is okay for SN1. Again, that nucleophile is not part of my rate determining step, so it doesn't have to be that great of a nucleophile. And then my last bit, our solvent. With SN2, we want an aprotic solvent. Remember, a protic solvent is going to stabilize my nucleophile, which would make it less reactive, so my rate would slow down. So we want an aprotic solvent. A protic solvent is good with SN2. That's going to stabilize my carbocation. It's also going to stabilize my nucleophile, but again, the nucleophile is not part of my rate determining step. So while that causes a problem with SN2, it doesn't cause a problem with SN1 because again, it's not part of my rate determining step. So we can stabilize our carbocation intermediate. That's the only part of our rate determining step that it's going to have an effect on, since that's the product of my rate determining step that is a favorable process. So some examples. I'm going to get us a set of conditions and we're going to determine, does it prefer SN2 or SN1? So our first alkyl halide here, and I'm going to put a methyl group coming out at us, which means I do have a hydrogen going back. You don't have to include that hydrogen because we are drawing skeletal structures. And then NaSH and DMSO. So kind of my thought process, the way that I like to go through this is the first thing I'm going to ask myself is what sort of alkyl halide is it? Is it methyl? Is it primary, secondary, tertiary? Is it allelic? Is it benzylic, etc.? So that's usually the first thing I'm going to do. And then I'm going to look at the nucleophile. Is it a good nucleophile, right? Is it a charged nucleophile? Or is it neutral? And then I tend to look at the solvent last. We're not always given a solvent. Sometimes you don't need it. Sometimes your nucleophile is your solvent. But if we are given one, I'm going to look at that. So is it aprotic or is it protic? Remember, aprotic is going to favor SN2. Protic is going to favor SN1. So on this structure, my alkyl halide, the carbon right here that my chlorine's attached to is attached to two other carbons, right? This carbon here and then this methyl group. So secondary alkyl halide. So that doesn't actually help us a whole lot. Secondary is fine with both SN2, SN1. Nucleophile, charged or neutral, well, I have sodium, which has an ionic bond to SH minus. Remember, if you have a group 1A cation, you can just get rid of it. You can ignore it. So SH minus, this is a charged nucleophile. So we know that SN2 definitely wants a charged nucleophile. SN1 doesn't really care. It could be charged or it could be neutral. So far this could go either way. So now I'm going to look at my solvent. DMSO is an aprotic solvent. A few videos ago, I gave us a list of aprotic solvents and protic solvents, and this was on our aprotic list. So you do need to be able to recognize that. So because my solvent is aprotic, this one is going to undergo an SN2 reaction. So that means when I draw my product, I need to draw my stereochemistry inverted. So for this one, the easiest way for me to draw the product then is I'm just going to straight up replace that chlorine with my nucleophile, and then I'm going to switch the configuration on that carbon. So, and it's good to check, it's really good practice to check your RS stuff. But if I do that, and then I make this one that's coming out at us, our hydrogen, and I put my methyl group going back, I'm now going to have the opposite configuration. It would also be really good practice. Remember, you guys are responsible for the mechanisms. I gave you the answer, so you don't have to worry about that part. I told you what type of mechanism it is. So I would go and practice that. Remember, when you do this one, you want to have that transition state shown, right? We're always going to show the transition state for SN2, and we want to make sure that the bond that we're breaking is 180 degrees across, right? Straight in line from that bond that we're forming. Another example for us. Let's do a cyclopentane, and then I have a bromine on there. And then we're going to be given ethanol. So same thing, I'm going to go through and I'm going to look at these primary, secondary, tertiary. So this one is a tertiary alkyl halide. Right, this carbon is attached to 3 carbons, my methyl group, this one, and that one. So tertiary. My nucleophile has that hydrogen on it. I can't just pop that off, right? It's a covalent bond between that oxygen and that hydrogen. So I have a neutral nucleophile. This nucleophile is also the solvent. You don't really need to know that, but it would be protic because I can form OH bonds. So this one is going to undergo an SN1 reaction. Remember, tertiary are not going to generally undergo SN2 reactions. It's too sterically hindered. So right away when I gave us tertiary in this chapter, we can just even really say SN1. At the end of chapter 8, in chapter 8 we're going to learn 2 types of elimination, and at the end of chapter 8 we're going to mix the 2 types of elimination with these 2 types of substitutions together. So you generally can't just say, okay, tertiary is going to be this, because tertiary is going to favor both of the eliminations also. My product, if it was chiral, which it's not, right? If I go left around my ring or right around my ring, clockwise or counterclockwise, it's the same thing. That's not a chiral center. So if it was chiral, you would want to make sure that you gave both products. However, it's not chiral, so I'm going to just draw this product. But if chiral, either draw both or put that little plus minus on it. So both enantiomers or diastereomers if I had two chiral centers, which I actually probably would. Let's do both stereoisomers. So both stereoisomers. Result. And I do want you to practice the mechanism. I'm going to do this one on account of, I want you to see how we're getting that product. A lot of folks will give me the wrong product. They'll actually put OH on there, but that's not what's happening. So I'm going to just do this mechanism real quick. Let's grab a different color here. It would be good practice though, to maybe even just pause the video for a minute and try this on your own. And then you can turn it back on and watch me do it. Okay, so my leaving group is going to leave. Remember, that's what we're doing first with SN1 reactions. Our leaving group leaves. I then have a carbocation intermediate. Sorry, that was supposed to be bonded. It's planar, so I'm not going to show that group coming out or back. It's in the plane of my iPad here. You would look for rearrangements. Anytime we form a carbocation, we want to look for rearrangements. This one wouldn't have any. If I was to do a hydride shift, I'd actually make it worse. It's tertiary right now, and I would end up with a secondary carbocation. We don't want to make it worse. We only want to do rearrangements if we can make it better. So we're not going to do anything. And then my nucleophile is ethanol here, this alcohol, and I have two lone pairs. So it's going to attack, I didn't leave myself much room, that carbon. Remember I said that if we have a neutral nucleophile, we usually have that extra step where we have to deprotonate it. So we're going to end up with that here. So I have this oxygen, it still has its hydrogen and its ethyl group and a positive charge. And then we need to deprotonate it. Again, you can use bromine if you want, you can use water, or you can use another one of these nucleophile, which is actually probably a solvent, and that's what I'm going to use. So it's going to take the hydrogen, and then remember, anytime you have a hydrogen that's already bonded to something, if you're going to draw a bond to it, then you need to break its original bond. Hydrogen can never have more than one bond. And then we finally get to our products. It's not chiral, so I'm not worrying about drawing wedges and dashes on that. Another example for us. So I have a cyclohexane, and then we'll put a chlorine on there. And then this nucleophile. So same sort of questions, primary, secondary, tertiary, allelic, benzylic. And then is our nucleophile charged or neutral? And then if we were given a solvent, we would look at that. So my alkyl halide is primary, right? This carbon that my halogen's attached to is only attached to one other carbon, so primary. I'm doing this nucleophile on purpose, right? We did this one in the last example, and we said that was a neutral nucleophile. This time, instead of having a hydrogen on there, I have a potassium. So I have an ionic bond, and I can ignore that potassium. Be careful not to get those two things confused, right? This is something entirely different. So what I have is a charged nucleophile. So primary alkyl halide, charged nucleophile. This is going to undergo an SN2 reaction. So my product, if it was chiral and this one isn't, But again, if it was, we want to make sure our stereochemistry is inverted. So that would be my answer. Again, please practice the mechanisms on these. If you have questions on them, make sure you ask me at some point. But again, you are responsible for the mechanisms, and the more you practice them, the better it's going to be. So CH3OH, and then let's do water. That's attached, just doesn't look like it. So same questions. I always look at my alkyl halide first. This time it's secondary. My nucleophile is neutral. That's a covalent bond between hydrogen and oxygen, so you can't just pop it up and give it a charge. And then I am given water, which is my solvent in this case, which is protic. So this one is going to undergo an SN1 reaction. And again, I'm going to just draw the product for you. I do want you to do the mechanism on this one though, because this one might look a little weird when I first draw it for you. And then we are going to have both stereoisomers for this one. So why do I think that you think that this one might look weird? This is the question of the day. Yeah, if we look at my reactant, right, I had my leaving group on the 3rd carbon, and here I have my nucleophile on my 4th carbon from the left. This one I would actually number it the other directions, 1, 2, 3, the 3rd carbon from the other side. But they're not on the same carbon. So what happened? Yeah, hopefully some of you guys said that your carbocation rearranged. So when you do the mechanism, do that. I do want to see that steps. So we had a carbocation rearrangement. And then also because we're doing that neutral nucleophile, you need to do that deprotonation step after you do the substitution. So again, please practice that mechanism.